Morning, everyone. So we're going to finish off our study on enthalpy changes. So far, we have 6 out of the 7 different ways. Today, we're going to introduce the one last way of finding enthalpy changes. Just like yesterday's lesson, we're going to switch gears from covalent compounds, specifically look at ionic compounds. Yesterday's lesson was a little bit more thorough because there were a lot of mini steps. I had to atomize, I had to ionize, electron affinity. There was a lot of little detailed steps to go through. We're going to see lattice enthalpy rear its head again in this section, but it's nowhere near as hard as we did yesterday. So just like yesterday, we're going to look at an ionic compound. I'm going to define for you a big equation. Yesterday it was lattice, and then we broke up the many steps. This time what we're going to look at, method number 7, is going to be called a dissolution cycle. We're going to look at dissolving the ionic compound. We're going to look at ionizing, dissociating the ionic compound. Because we can't do that directly, we're going to figure out what are the mini steps we need to go around that way. Just before we get into that here, I do want to show you a nice little schematic here of the pages in your data booklet. So yesterday for the MgCl2 question with the Born-Haber cycle, you can find some experimental lattice enthalpies. They do remind you they're going to lattice enthalpy, they're going to use the endothermic direction. We were specifically looking at if I just doing +1 and -1 here, just like you do with your bond enthalpy cycle, you just crisscross, let's say Na and Cl, oh that's going to be 790, all quoted in kilojoules per mole. So those are sort of +1 and -1. So these are alkali metal halides. And you have just a handful of other compounds here in case you have like alkaline earths, in case you have oxides, and in this case your fluorides as well. You might just be able to read these. There's no crisscrossing. You just figure out that there. You'll notice, and I want to emphasize this here, lattice enthalpies here, these are all positive values. Positive, right, for endo, right? Positive for ripping apart. There's no reason for your lattice, which is happy the way it is, there's no reason for your lattice to separate into the gas ions without you putting in a lot of energy. So that one there is always positive. In today's lesson here, we're going to use 2 other tables, table 19, table 20. Table 19 actually involves the enthalpies of aqueous solutions. So this one here is going to be our big equation. It's going to involve starting off with our solute. This one here is going to be our solid. And in general here, we're going to take our solid, and I'm going to try to I'm going to dissolve it into the sort of aqueous ions. So again, I want to be breaking apart the solid. I want to have some measure of the strength of the lattice. In this case here, when it separates, it ends up becoming in the aqueous state. You'll notice for this one, in contrast, while lattice enthalpies here, if you want to put them all in the gas state, it definitely is endo. Sure, some of these upon dissolving is actually endo. Some of them are actually exothermic as well. This actually does have some implication later on next year when we do equilibrium reactions. Depending on whether we're endothermic or exothermic, it actually does change my solubility. Sometimes, or generally we say when we heat things up, things become more soluble. It's possible if some of these here have the heat term on the wrong side, that if you end up heating the temperature enough, it can actually become less soluble. So that has to give rise to, based on the endo and exothermic of these solids here. The last sort of mini step here we're going to need, that we're going to see in this lesson here, is what's called the enthalpy of hydration. Enthalpy of hydration involves you're going to have a bunch of gas ions, and what we're going to do is we're going to surround them with water. Right? We're going to bubble the gas water. We're going to bubble the gas into water, and we're going to let water as a ligand surround these ions, and that's called hydration. Because that always puts the ions in a more stable state, right? The ions aren't just loose trying to spread throughout the container. Now they're actually being stabilized by your ligands. What we're going to see in contrast, these enthalpies of hydration are typically going to be exothermic. It ends up putting you into a more stable state here. So exothermic means the delta H is always going to be negative. And as we're going to see in today's lesson, the solution enthalpy, a dissolving reaction, is made out of a lattice enthalpy that's always positive and a hydration enthalpy that's always negative. Depending on which of those ones are larger, it would amount to a solution enthalpy sometimes bigger than 0, sometimes less than 0. So without further ado here, let's take a look at method number 7. Nowhere near as hard as the one we did yesterday. So this one here is called the dissolution cycle, a dissolving cycle. Just like yesterday's lesson, I'm going to introduce to you what the big equation is. So in this big equation here, I'm going to introduce you the term. They can ask you to define any one of these, by the way. The big equation here is, I want you to define the standard enthalpy change, or heat of, doesn't matter, standard enthalpy change of solution. And in this case here, I'm sort of using solution as a verb here. I'm sort of making a solution by dissolving. And again, it involves ionic compounds. In this case here, I can symbolize it delta H standard state here. I can put SL for solution. Again, we are looking at the energy change, right? Enthalpy is energy, specifically of the particles themselves. So in this case here, we're looking at the energy change, or the heat of, the energy change energy change when 1 mole, again, there's that little pesky 1 mole show up again. We want to quote these values here for 1. I'm going to bear with the odd fraction every now and then, so that if I know this is always for 1 mole, I can scale it up or down accordingly. So this is the energy change when 1 mole of compound or species, you can even say solute, because that's usually the terminology we use for dissolving. When 1 mole of solute is dissolved, sometimes they want to emphasize here into excess solvent. That's a little bit redundant because I know the solvent by definition is already the thing that's in greater quantity, into excess solvent. However, they do like this terminology here to make an infinitely dilute solution. Right. At the end of the day, we're doing dissolving, but let's see some of these technical notes here. What is an infinitely dilute solution? So let's just start off. Say someone hands you some NaCl, so just table salt. You would understand that although in the compound, every one Na has one partnering Cl, we know all ionic compounds end up forming a lattice. So what's going to end up happening here is we're going to have a bunch of positives, negatives, right? So this is the lattice. It's solid, it's perfectly happy. What we're going to do is we're going to drop this here in water. As I drop this in water, yes, I know the water is good enough to actually break apart these, and it's providing the energy needed to rip apart these ionic bonds here. We're going to see that in a little more detail. But what I want to show you here is water doesn't break it up all at once. So perhaps water's first cut, it maybe only manages to cut off maybe this one green. So what's going to happen here, let me just draw a few sort of time-lapse picture of this one here. So let's say I have most of my lattice here. Most of it's still intact, right? It hasn't really managed to dissolve yet, but you managed to dislodge that plus. And you continue to fast forward the clock here, and basically water is going to come in and going to make another cut here. It doesn't take that long here because NaCl here is very soluble. Maybe I end up cutting off that top part here. This positive and the negative, they're separated. Maybe this bottom part here still is positive like this. And over time, if you just keep going, we're going to eventually form a solution where all the bonds themselves are actually separated. All the positives, I had 3 greens before, I have 3 reds afterwards, and you now see none of the cations are now beside the anions anymore. This is what I refer to as an infinitely dilute solution. An infinitely dilute solution has had the chance where water has actually broken up all the bonds that there is no further energy change. No further energy change since all the ions are separated. Right? So you can just use that language of an infinitely dilute solution. That's what the standard enthalpy solution comprises of. When I write this out here in terms of a reaction, I'm going to have, starting off with 1 mole of NaCl, I'm going to dissolve it so fully, right, so completely in water here that the Na plus separates from the Cl minus. In this case here, these two here are going to be in the aqueous state. Back in chapter 1, we had called this here a dissolution reaction, a dissociation reaction. Dissociation involves, well, everything breaks apart. In this case here, it breaks up, right? The Na is no longer connected to Cl. The lattice doesn't hold itself together anymore. We also, in chapter 1, had called this an ionization. I don't particularly like that language because ionization, in some sense, yes, it does show off the charges, but I do want to emphasize here, notice those charges were initially present already. When I see NaCl, when I wrote the ionic compound, sure, we had worked out our formula unit, worked out a ratio so that there was no overall charges, but it's true, the Na is still positive, the Cl is still negative. It's just now that water has actually overcome these intermolecular forces, broken apart, dissociated these ions here, then maybe let's better yet say, ionization ends up just showing charges, shows the charges. So it reveals the charges, although those charges were already there. When you look at that expression here, you might see, well, this looks very familiar to what we did yesterday. Yesterday, we also took an ionic compound, and we also, this is going to be the start of what's called a dissolution cycle. Yesterday, we took the solid ionic compound, and we ended up getting Na plus as a gas, Cl minus here as a gas. That was our big equation. That was called lattice enthalpy. So delta H lattice enthalpy. So that was all the mini steps here. I needed to flip the formation, I needed to atomize, I needed to ionize, electron affinity, lots of those mini steps, but eventually that's what it did. It took the lattice and it put these guys here in the gas state. This process here is always going to be endothermic. That's why on table number 18, these ones here were all positive values. It's a really, really high energy requirement for you to actually do that. In this case here, our dissolving reaction for today's lesson, we're going to see that there's one added step. We don't just start off from lattice enthalpy, we then surround the ions. These ions here are super unstable, especially when they're the gas, especially when they're so separated. What we're going to do is we're going to finish off the cycle, and we're going to put on an enthalpy of hydration. Enthalpy of hydration involves, let's bubble these ions here into water, let's let the solvent actually surround it, let's let it actually stabilize the ion, let's let it pay me back a little bit here. Those ones there are on table number 20, and that actually completes for us. In the big equation, we had called this one here delta H solution enthalpy. That's the dissolving reaction. The dissolving reaction here is sort of part lattice enthalpy, just heat it enough so the ionic bonds break up, but also factor in how much money I'm getting back, how much that stability and that surrounding the anions and cations actually pays me back to overall give me a solution enthalpy. So table 20 gives you your hydration enthalpies. You're going to find, as we said earlier, hydration enthalpies are always going to be exothermic. It's always going to release energy. The overall solution enthalpy may be endo or exo, depending on which one of these is more. Let's use the money analogy here. The lattice enthalpy is, the lattice is very strong. So it is going to be a huge upfront cost. Let's say I ask, oh, give me $100 and I'll rip this apart for you. You might say to me, well, I don't have $100. But what if I guarantee you, after you give me $100, after I do this process, I'm going to give you $150 back? Would you do it? Well, of course, right? Even though the $100 here was an upfront cost, that's similar to sort of melting and boiling, try to do that physical change of breaking it apart. But if I'm guaranteed to always get some money back, it sort of lessens the impact. In that case, with my analogy, $100 in and $150 out. Great, I'm net of $150, so therefore that solution enthalpy would also be exothermic. It may not necessarily pay you back completely. It may be, well, I'm going to ask you for $100 to rip this guy here apart, but I'm only going to give you $80 back. Again, yeah, I'm sure I'm out $20, but being out $20 here is not as high an upfront cost as, say, being out $100. So that's actually specifies the difference. Why does table salt dissolve at room temperature? But why does it, in terms of melting, why does melting or boiling, why does that take upwards of 700, 800 degrees? Why doesn't it melt until we have such dramatic heat changes? Melting is sort of like trying to do this lattice enthalpy here without being paid back, whereas the dissolving reaction here, when you dissolve the ionic compound, sure, you're still ripping up a positive negative, but given how much I actually get back from hydration, it actually lessens the upfront costs. So we're going to practice a few questions later on that deal with this. This cycle here is called the dissolution cycle. Let me also just write down just more technical definitions for, we mentioned the dissolving reaction sort of couples the lattice, couples the heating it up enough to break apart the ionic compounds. Let me just define this latter one for you here. This delta H lattice is usually called the standard heat of hydration. So in this case here, you're used to the definition by now. This is the energy change when 1 mole, there's that pesky little 1 mole shows up again. When 1 mole of your solute, 1 mole, enthalpy of hydration is when 1 mole of, let me actually specify here, 1 mole of your gaseous ions is surrounded by, in this case here, water. If water is your solvent, we can use the terminology of hydration. The more generic language here is you can call it standard heat of solvation, is basically being surrounded by whatever the solvent is. We're going to always assume that it's water just for simplicity. So the picture here is not that hard. So You have your beaker, your Na plus, let's say, in the gas state is really unstable. Being charged is unstable. But if I manage to bubble this gas here underwater, this Na plus here gets surrounded by water as a ligand on all sides. The water ligand here actually helps to stabilize. Right? Remember, octahedral from chapter 3 was the best geometry. It does this sort of dative bonding. It ends up forming a much larger complex. Even though water itself is a neutral ligand, water can't get rid of that positive charge. You can write down here, the complex helps spread out charge. Use that hot potato analogy here. Sodium doesn't necessarily want to hold the Na plus, the positive charge all to itself, but once it's become complex with ligands, once it's a much larger species, it can pass that hot potato around. That charge density can spread around a much larger ligand. The water would show off its other side to the chloride, right? So water is polar. The H side tends to be more positive. So in this case here, it would be the oxygen side that's pointing towards sodium. For the chloride, exactly the opposite. The hydrogen sides would point towards chlorine. So that one there, like we mentioned, is always going to be exothermic. It's going to give me some of the money back, and it's going to lessen that upfront cost. That's about it for this dissolution cycle. So let's just try out a question here. Let's see if we can get the question. Let's say NaCl solid. Let's truly dissolve it, Na plus, aqueous, and Cl minus. Let's say this one here wasn't on the table. It actually is, but we'll come back to it. What I can do with the dissolution cycle is I can imagine first latticing enthalpy in this NaCl, Na plus gas and Cl minus gas. When I lattice enthalpy here, that's sort of like melting and boiling. That's sort of the endothermic process. That's on table number 18. And what we can do is hydration is per element. So I can do the hydration enthalpy of sodium and the hydration enthalpy of chlorine. Both of those should be exothermic. Both of those are on table number 20. So here's our Hess's law again. Hess's law says if I start here and I end here, I don't have to go the direct path. I can actually go this sort of roundabout path. I don't memorize any of these equations. It's easy enough to just draw the cycle. But from the Hess's law, it says the delta H solution, what I highlighted in that blue there for you. So to get from that solid lattice to the aqueous ions, you could imagine doing lattice enthalpy first. That's the first step in your green path. And then you can imagine doing hydration enthalpy plus the hydration of sodium plus the hydration of chlorine. So let's look up some of these values here. We had them at the top just to show you where they are. So lattice enthalpy of NaCl. I look at Na, I look at Cl, it was 790. So that one there is going to be 790. Hopefully you have the table in front of you so you don't have to do the scrolling. 790 plus the hydration enthalpy. We're going to do sodium and chloride. So sodium is going to be negative 424, negative 359. So negative 424, negative 359. All of the enthalpies on the data booklet are quoted in kilojoules per mole. And we basically add those numbers up, and we manage 790 minus 424 minus 359. This one gives me 7 kilojoules per mole. So if you wanted to just melt it and boil it, melting would have taken an upfront cost of about 790, give or take, okay, just for reference sake. Dissolving, however, the reason why water is no problem dissolving at room temperature, not that hot, it's because in terms of the water actually surrounding it and actually paying you back, water actually lessens the cost. The dissolving is sort of like the melting, right? I'm using that very loosely. Melting would actually make like a molten, like a lava of NaCl, but definitely dissolving is not just the upfront cost. I don't have $790, but if I said, what if I give you some money back? What if you only need to pay me $7? It drastically drops that. So that's what we call a dissolution cycle. Normally they give you a compound where solution enthalpy isn't anywhere. So there we go, 7 kilojoules per mole. Just for reference, on table number 19, we've been saying there are the odd solution enthalpies here. Because NaCl is such a common compound, I would expect to see it. The enthalpy solution for NaCl is quoted at positive 3.88. So first thing is you'll notice that it's fairly similar, right? That's a good sign. We're still slightly endothermic. We're still positive on both sides, but you notice that they're not exactly the same. The reason for this here is if you look at your terms, because your lattice enthalpy here would have come from that Born-Haber cycle, it's possible, like we said, it's possible any discrepancy is due to covalent nature. Even though NaCl should be a very ionic bond, there's no guarantee that it's necessarily 100% ionic. There may be some overlapping between the orbitals. So let's just finish off with one last question here. This one here shouldn't feel as hard as the cycle we did last day. So I want you to calculate, same idea, calculate the solution enthalpy. I'm going to give you the compound CaCl2. They might imply here using a dissolution cycle. Using this dissolving cycle, show me the mini steps and all the part steps that I would need. I would just draw out a cycle. So start off with the solid CaCl2 as a solid. If I solution enthalpy this guy, if I dissolve it completely, I'd expect to get Ca2 plus, 2Cl minus. They would be in the aqueous form. I'm going to do the lattice enthalpy first and essentially rip this guy here all apart. That one there is on table number 18, and I'll let you finish this off here. You're going to do the hydration of calcium and similarly the hydration of chlorine. I do have to double it because this one here is quoted per mole, so there I can scale it up by 2. So try it out for yourself here. I don't believe you have it on table 19, so you do have to use table 18 to find the lattice enthalpy and then table 20 to find the hydration enthalpies. So let me just write that one last statement for you here. For the solution enthalpy of CaCl2, you would follow the lattice arrow as is. You would add up the hydration arrow for calcium, and then you would add up twice the hydration for chlorine. All right? So keep practicing through your questions. That does wrap up our study with enthalpy. We're going to have 2 last lessons, one to switch over to take a look at entropy, and then we're going to finish off this chapter with spontaneity. If you have any questions, just let me know. Thanks, guys.